All right, in today's lesson, we're going to be exploring electric fields, building on what we learned in grade 11. So recall that an electric field is that region of space that surrounds an electric charge. And an electric field is really that region of space where another electric charge would experience an electric force. Recall that fields are required to exert non-contact forces, of which electric forces are non-contact. So there are two types of charges, as we know. There is a positive charge and a negative charge. By convention, electric field, which is designated vector E, moves away from a positive charge. Likewise, electric field is directed towards a negative charge. So the direction of electric field is always away from a positive charge and towards a negative charge. Remember, it is defined as the direction at which a small point charge, Q0, would experience an electric force. In this case, if Q0 is defined as a very negligible positive charge, the vector would be pointing away like that. Likewise, if we did a test charge over here, it would be pointing towards the negative charge. So recall that electric fields are directed away from positive charges and towards negative charges. We learned in grade 11 that electric field is defined as a ratio of electric force per charge. It is defined as the amount of electric force divided by the electric charge. This also allowed us to then define an electric force if there is a uniform electric field. F would equal Q times E if we just isolate F. And that's what we did in grade 11. Okay. So the unit, again, recall, of electric field is newtons per coulomb, because force newtons divided by charge coulombs, newtons per coulomb. Now, electric field is a vector, and therefore, if there are multiple charges in the system, we can get the vector sum of each individual electric field in one dimension or in two dimensions. Again, if there's two-dimensional, then it's going to be vector components. So again, we're using the vector components a lot here in this unit. So it's just building on what we already know about how to add 2D vectors. Okay, so how about a non-uniform electric field? So how about electric field around a point charge? Okay. So the electric field around a point charge is non-uniform. Okay, so there has to be a different definition, and we use Coulomb's law. So if electric field is defined as electric force over charge, and here, if we refer to the electric force right there as Coulomb's law, KQ over R squared. So we take Coulomb's law force, KQ over R squared divided by Q. You'll notice that the the test charge cancels out, and we're left with electric field equaling K times Q over R squared. So that is the definition for electric field, KQ over R squared, where Q is the charge on the sphere or the object or the other charge, and R is the distance. Note in diagrams, the electric field intensity at any point is indicated by the relative distance. When the intensity is strong, the field lines are closer together, and more widely spaced fields indicate a weaker field. Remember the field line density. The closer the field lines, the stronger the electric field. So we looked at charge systems in grade 11. If they're like charges, again, if there's a dipole here, two charges, the electric field will kind of look like this. Notice the lines are supposed to actually make contact with the surface. So just make sure that you show the lines making contact. So OA, so they're angling outwards, and notice there is 0 field density in between. Backing up, the only difference, if this was negatives, then the arrows would be going towards. If you have a dipole where there is oppositely charged, plus minus or minus plus, again, notice it goes from plus to minus, okay? And there is some bending of the field lines, okay? And remember the parallel plate apparatus, charged parallel plates, which we'll get into more detail later on, but we have, this is a uniform electric field, which means the field lines are evenly spaced out. Again, going from positive plate to the negative plate. Basically, that's that. Okay, so this is a review all from grade 11. Okay, these diagrams. So really what we're going to do in today's lesson is look at some examples. One, calculating the electric field for one charge, and then in a 2-charge system, one-dimensional, and then a 2-charge system where it's 2-dimensional, where the point is not in the same dimension. So that's what we'll be looking at here. So first example, a positive charge, 6 times 10 to the negative 6 coulombs, is in between 2 parallel plates and experiences an electric force acting to the left. So if we draw a free body diagram, okay, we have a positive Q and experiences a force to the left. Okay, what is the magnitude and direction of the electric field on this charge? So we're going to use the field E equals Fe divided by Q because it's between 2 parallel plates and therefore it's uniform. But how about the direction? Remember in grade 11 we learned that positive charges experience an electric force parallel to the field. So the field arrow must be going to the left. If this was a negative charge experiencing a force to the left, then the E would be to the right. But because it's a positive Q, E is parallel to Fe. Okay, so now it's just a matter of calculating the force. Calculating the electric field. So E equals F divided by Q. Which equals 5.2 newtons divided by 6 times 10 to the power of negative 6. And we can get our answer. (5.2) divided by 6, 10 to the negative 6, gives us 800. If we're going to 2 sig figs, this would be 870,000 newtons per coulomb. 870,000 newtons per coulomb, and the direction would be left. Okay, and that would be a review from what we did in grade 11 for a uniform field. So example 2, we're going to look at a non-uniform field. So when we're looking at the electric field intensity and we were given a distance, okay, we have to use the previous definition, which is KQ over R squared. So non-uniform means we use KQ over R squared. So example 2 is non-uniform. can figure this out. To get the E, this will be equal K times Q divided by R squared. And we can get the magnitude very easily. So this is going to equal 9 Coulomb's constant. So 9 10 to the power of 9 times Q, which is 1.6, times 10 to the power of -8, divided by R, which is 0.5 meters. And we're going to square that. Okay. So now we can figure out the magnitude. Pretty straightforward. So 9 times 10 to the power of 9 times 1.6 times 10 to the power of -8 divided by 0.5 squared gives us 576 newtons per coulomb. Now we need the direction. So we have a sphere that is positively charged. Whoa, it's too big. And we have our point P, and we want to know right there, that's point P. Now we want to know what's the direction of the field, of the electric field. So we know this is a positive charge because it says it's a positive sphere. So the E must be directed away. We don't know where the P is. It doesn't say where exactly is, but we know that wherever P would be, wherever that point is, the field will point away from the sphere. So back to here, our direction, we would just put away from the sphere. That would be our answer. And I guess we'd have to round our sig figs. So that should be 580 newtons per coulomb. Okay. Hopefully that's pretty straightforward, using Coulomb, like using the force KQ over R squared to get the electric field. Now we're going to look at adding the electric fields when we have more than one charge. So we have two negative charges. So we'll refer to these QA, QB. So we could draw a diagram. So you got A and you've got B, and then you've got your point P. It's exactly in the middle. So point P would be here. Okay, hold on. We'll draw the R between the two. There we go. We know that's 30 centimeters. And point P, it says, is exactly in the middle. Okay. So if these two charges, A and B, are 30 centimeters apart, then P must be halfway. So we have 0.15. Whoa, that's terrible. I'll just type that in. So here we would have 0.15 meters because 15 centimeters, right? 5.15 meters. And then this would be 0.15 meters as well. Okay, so we have our two distances. We know QA and QB. We know they're both negative charges. So if we did a field vector diagram, not a free body diagram, but a field vector diagram, the electric field due to charge A would be towards A because it's a negative charge, and B is also a negative charge. So the field due to A would be going to the left. So that'd be the field due to charge A. As well, the field due to charge B would be going to the right because it's a negative charge. That'd be the field due to charge B. So notice that the two fields are in opposite directions. So one of them is going to be the positive direction and the other one's going to be the negative direction. So by convention, to the right is positive. So we will say that this is to the right. Therefore is positive, not due to the positive charge, but just because it's the positive direction. And this is the left, which by convention is the negative direction. So when we add these two fields, EA is going to be negative and EB will be positive. Okay, so our first order of business is to find the two fields. So KQ over R squared. Okay, so EA will equal KQ divided by R squared. Nice. Okay, so that's going to equal 9 times 10 to the power of 9, as you already know. Times QA. QA is 3.2 times 10 to the power of negative 9. 2 times 10 to the power of negative 9 divided by R, which is 0.15. We're going to square that. Okay, and we can figure out the field due to charge A. Okay, so 9 times 10 to the power of 9 times 3.2 times 10 to the power of negative 9. And we divide that by 0.15 squared. We get 1280 newtons per coulomb, and we'll say to the left. So 1280 newtons per coulomb to the left. Okay. To save time, I'm going to copy this. Okay. So I'm going to copy this, paste it over here, and I'm just going to change the words. Okay, so, and I'll do, may as well change the color too. So we'll do this in brown. Okay, so the field due to charge B will equal KQ over R squared, and now we have to use QB. QB is 6.4 times 10 to the power of negative 9. So this will be 6.4 times 10 to the negative 9 divided by the R squared, divided by the distance, so squared. So now we can go ahead and calculate that. So 9 times 10 to the power of 9 times 6.4 times 10 to the power of negative 9. We divide that by R squared, so 0.15 meters squared, and you get 2560. Interesting, from a proportion standpoint, the distances are the same. The only thing that's different is the Q is doubled, so we would expect then that the field would be doubled if we double the charge. So we get we get 2560, 2,560 newtons per coulomb, but B is to the right of the point and it's negative charge, so the field due to charge B is going to the right. Okay. Now we have to figure out our total, our E total. So the total field is going to be due to the field due to charge A plus field due to charge B. So this is going to equal, now this is going, wow, technical difficulties. This will equal, all right, field due to A is going to the left. So we're going to say negative 1280 plus field due to charge B is 2560. It's to the right, so it's positive. So we're going to take negative 1280 plus 2560, and you get positive 1280 newtons per coulomb. In other words, the total field, if we're going to draw a vector arrow, if this is the point, then the field would be going to the right. That would be the total field, 1280 newtons per coulomb to the right. So again, we're just figuring out the electric field due to each charge, and then we're adding them as vectors, which this is nothing new, that we know how to do this already. So hopefully that makes sense to you. So that is looking at a one-dimensional example. Our final example for today is to look at a two-dimensional example. So here we have a two-charge system, QA, positive 9 microcoulombs, and QB, 12 microcoulombs. We have the separation distance of the two charges, and we know where the point P is. It's directly to the east of point of QB. We don't know where it is relative to point P. We do know that it's some distance south, I guess you would say southeast. So as you can probably see here, we've got a right angle triangle. We need this hypotenuse to represent the distance that we're going to use between point and QA. And then we're going to need to get the angle, so we know that it is south of east, or we could use the angle inside, and that would be east of south. So however you want to work it, we are going to have to figure that out first. So we are determining the magnitude and direction of the field due to point P. So if we want to start with how we're going to figure this out, the electric field the total electric field is going to equal field at point A, the field due to charge A added to the field due to charge B. Okay. And we know that field is equal to KQ over R squared, so we need to find the distance. So the first things first, we need to find the distance due to charge A, and that's the hypotenuse. So A squared plus B squared equals C squared, as we know. So the distance due to charge A squared, this distance here, hypotenuse, is going to equal 0.64 squared plus 0.84 squared. And we're going to take the square root, so the field due to charge A, calculate it right now. Okay, so 0.64, whoops. 0.64 squared plus 0.84 squared. Okay, and then we take the square root of that, and you get 1.056 meters. 1.056. Good. So if we were going to label this then, there we go, that would be 1.056 meters. Okay. Next thing we need is the direction. So we need that angle theta. So the angle theta is going to be inverse tan, opposite over adjacent. So inverse tan 0.84 over 0.64. So theta will equal inverse tan opposite 0.84 divided by adjacent 0.64. And we can figure that out as well. So inverse tan opposite 0.84 divided by adjacent 0.64, and you get 53 degrees. That would be east of south. So we'll just use that as our direction. It would also, if you wanted south of east, then you would just subtract it from 90 and get 37 degrees south of east, but we'll stick with the 53. Okay, good. So next we have to find the charges. So just bearing with me, I don't feel like typing that all out. Copy paste this. Okay, so change that to an A, and we'll change that to a B. Okay, so KQ over R squared. So okay, so QA is 9 microcoulombs. So that would be 9. Change this to blue. So that'll be 9 times 10 to the power negative 6. And the distance at A is 1.056, so divided by 1.056 squared. Okay, and you have to get a new direction there. And QB is 12 microcoulombs. So we change that to a 12 times 10 to the power of negative 6 divided by the distance is 0.84. So 0.84 squared. And then we'll redo that. And it's positive, so the direction would be to the right. Okay. Okay, so now we can calculate this. So 9 times 10 to the power of 9 times 9 times 10 to the power of negative 6. And we divide that by R squared. So 1.056 squared. You get 72,637. So 72,637. 72,637 newtons per coulomb. And the direction will be here, 53 degrees east of south, because it's positive and it's going to be directed downwards. So it's going to be the same, it's going to be that direction. All right, so the QB kq over r squared. So 9 times 10 to the power of 9 times 12 times 10 to the power of -6 divided by r squared, 0.84 squared, and you get 153,061. 153,061 newtons per coulomb to the right. Okay, so now we have to add these two vectors, and you'll notice that they're two-dimensional. So we are going to need to do a vector chart. In this case, our vector is field. Okay, so vector x, y. Okay, so we have field due to charge A, field due to charge B, and then the total field where we add the two. Okay, so let's begin. Due to charge A. So here, we could draw the vectors if we want to visualize, which I'm fine with doing so. So the field due to A is going to, oops, not that way. It's going down like that. And the field due to B is going to the right. So here, what we're going to have to do is look at our triangle. So I'll put this in a different color. Our y is going to be the adjacent side, and our x is going to be the opposite, because our theta of 53 degrees is right there. Okay, so our 53 degrees is there, and there's our y, and there's our x. So the x is the opposite side, which we know is going to be sine. So EA is positive because it's going to the right. 72,637 sine 53. And our y is going south, so negative 72,637 cos 53. Okay. Our field due to B, QB is to the right, so the x is positive 153,061, and of course the y value would be 0. So we can add these vectors up. We would go 72,637 sine 53. We will add 153,061, and you get 211,071. We're going to round because we're taking it to scientific notation. So our rounding will be about in here when we do it at the end. So I'm fine with that. So 211, positive 211,071. So plus 211,071. And our y, as we know, is going to be going south. It's simply 72,637 cos 53. And you get negative 43,714. Negative 43,714. Okay. So now that we know the x and the y, we can draw our triangle. So x is positive. And the y is south. and our hypotenuse is there. So there's our x, there's our y, there's our theta, and there's our E total. Okay, so a squared plus b squared equals c squared. So E will equal 211,071 squared plus 43,714 squared. I don't feel like typing this, sorry, and then we will take the square root. Okay, but I will type the answer. Okay. That will equal, okay, 211,071 squared plus 43,714 squared. And then we take the square root, and you get 215,550, 215,550. Okay, good. Now our angle theta, inverse tan, opposite 43,714. Divided by 211,071. Again, I'll type in the answer. Inverse tan, 43,714 divided by 211,071. You get 11.7, 12 degrees south of east. So that would be 12 degrees south of east. Okay. So our final answer then, the total electric field at this point, due to charge A and B, we'll look at our sig figs. We need one sig fig. So it would be 200,000 for rounding the two. So 200,000 newtons per coulomb, 2 times 10 to the power of 5. So 200,000 newtons per coulomb. The direction would be east, 12 degrees south, or 12 degrees south of east. We have just completed determining the total electric field at a point due to two charges. So notice that is very similar to the total force with Coulomb's law. You find the individual fields, and then we add them if they're two-dimensional. So it's kind of the same procedure. So hopefully this is clear to you. I wish you all the best of luck working through these examples. Your homework would be to complete the electric fields worksheet. Tomorrow is a work period. There will be text questions assigned, and I'll also be giving you an electric fields concept check. That'll be due Thursday. So good luck, and if you have any questions, don't hesitate to email me.